Hey everyone, and welcome. I am so incredibly excited to share this explainer with you today. We're about to embark on a deep dive into the very heart of computational problem solving and algorithm design. Seriously, if you've ever found yourself wondering how massively complex software actually gets built, like how we get from a messy, real-world problem to a flawless digital solution, well, you're in exactly the right place. Today, we're demystifying the architecture of logic itself.
So, here's our blueprint for this explainer. 1. The illusion of coding. 2. The four-step pipeline. 3. Designing the blueprint. 4. Controlling the flow. 5. Testing and efficiency. And finally, 6. The architectural discipline. Let's get right into it.
Part 1. The illusion of coding. Redefining computer science.
To kick things off, there is this fantastic quote by computer scientists A. Aho and J. Ullman that hits the nail on the head. They say, computer science is a science of abstraction, creating the right model for a problem and devising the appropriate mechanizable techniques to solve it. Now, did you notice what's actually completely missing from that definition? Typing code. The absolute core of computational thinking isn't coding, it's abstraction. It's about how we model the real world.
Think about a massive intersecting railway grid. Computers can't just magically solve those routing problems on their own. I mean, yes, they are incredibly fast, but they're also perfectly literal. They need incredibly precise, step-by-step instructions. Writing code, or programming, is really just the final translation step. The actual heavy lifting, the real problem solving, that happens in the human mind long before a single line of code is ever typed out.
Moving on to Part 2, the four-step pipeline, a roadmap for solutions.
Whenever you're tackling a problem, there's a reliable four-step pipeline you want to follow. Stage 1 is analyze, where you really nail down your inputs and outputs. Stage 2 is design, and this is where you create the algorithm. Stage 3 is code, which is just that translation phase we talked about. And Stage 4 is test and debug. So, the magic really happens right there in Stage 2. The design phase is where the actual problem solving takes place. But here's the catch. You literally can't design a solution if you don't understand the problem first. Which brings us to a golden rule.
You absolutely must respect the GGO principle. Garbage in, garbage out. Put simply, the correctness of your output relies entirely on the correctness of your input. If your problem definition back in Step 1 is flawed, well, your perfectly designed program in Step 3 is just going to execute the wrong solution, flawlessly. You've got to get those parameters right from the very start. It helps to think of that first analysis step like a giant input-algorithm-output conveyor belt. You grab your raw data, all those scattered pieces, feed them into the algorithm machine right in the middle, and it spits out perfectly sorted, useful information on the other side. But to build that machine, you have to really read the problem statement, list out every component, decide on the core functionalities, and know exactly what's going in and what's coming out.
Okay, Part 3, designing the blueprint, the anatomy of an algorithm.
So what exactly makes a good algorithm? Obviously, it needs initial input and a desired output. But crucially, it needs 3 specific traits. Precision, meaning every single step is explicitly defined. Uniqueness, where the result of each step depends only on the steps that came right before it. And finiteness, the logic actually has to stop at some point. Oh, and fun historical side note, the term algorithm traces all the way back to the Persian mathematician Al-Khwarizmi, around 850 AD. So we are talking about ancient, brilliant logic powering our most modern technology. When we're drafting these algorithms, we typically lean on 2 main blueprint languages well before we boot up a code editor: flowcharts and pseudocode. A flowchart is highly visual. It uses standard geometric shapes to map things out for human planning. Pseudocode, on the flip side, uses textual instructions with casual English keywords, like input or compute. The beauty of both is that they are language agnostic. They let us humans hash out the logic safely away from the strict, unforgiving grammar of actual machine code. For this explainer, we're really going to lean into the visual side. Let's do a quick run-through of the visual grammar of a flowchart. You've got your oval capsule, which marks where the whole thing starts and stops. Parallelograms handle your data, inputs and outputs. The diamond? That one's absolutely crucial. It's your decision point for true or false branching. The rectangle is your workhorse. It represents a single process or action. And finally, the arrows hook the whole shebang together, letting you see the exact flow of control at just a glance. Which leads us perfectly into Part 4, controlling the flow, sequence, selection, and repetition.
It's kind of wild to think about, but pretty much every computational process ever designed boils down to just 3 fundamental structures of control flow. First up is sequence. The This is moving in a straight line, executing statements exactly one after another, like when you calculate an area. Second is selection. This is choosing different paths based on a condition. Think of a fork in the road. And third is repetition, running tasks over and over in a loop, kind of like a roundabout, until a certain condition is met. Let's zoom in on those last two for a second.
Selection logic is all about multi-conditional branching. Imagine drawing playing cards. Using conditionals, we check possibilities sequentially. If the shape is a diamond, do this. Else, if the shape is a heart and it's a number, do that instead. The big takeaway here is that the moment a condition is met, the program takes that specific branch and literally ignores everything else. It's your ultimate decision maker.
Then we have repetition logic, specifically the incredibly powerful while loop. We use this when we have absolutely no idea how many times a loop needs to run. Say you have a condition gate. While a number is not equal to 0, the program enters the loop, crunches some math, and loops right back around. It'll stay trapped in that cycle forever until the user finally inputs 0. That triggers the false branch, letting the program exit and print out the average.
And understanding sequence, selection, and repetition is such a game changer, because when you combine them, you can build incredibly complex architectures. Take a look at a massive national railway reservation system. It looks totally overwhelming, right? But the secret sauce is decomposition. We divide, conquer, and scale. These giant systems decompose into manageable logical chunks, like billing or train info. You solve each subproblem using your basic sequence, selection, and repetition, and then use that structural logic as the glue to hold the entire railway system together.
All right, part 5. Testing and efficiency. Perfecting the blueprint. So before we code, we start by verifying our blueprint manually. We call this a dry run. Imagine you're tracking time. If we just blindly add 4 hours and 50 minutes to 2 hours and 20 minutes, our tracker outputs 6 hours and 70 minutes. Boom, crash. Obviously, 70 minutes is an invalid state for a clock. But by doing a manual dry run, literally tracking our variables step by step on paper, we catch this logical flaw right away. The fix is super easy. Just drop in a simple selection block, an if statement, to convert those extra minutes into hours. Dry runs catch errors when fixing them is still cheap and easy.
But this brings up a really fascinating question. Let's say you have two totally different algorithms and they both successfully output the exact right answer. What actually makes one algorithm better than the other?
The secret lies in algorithm efficiency. It all comes down to the ultimate trade-off, time complexity versus space complexity. There's almost never one perfect algorithm. Maybe method 1 barely uses any memory, but it takes ages to process. Method 3, on the other hand, is lightning fast but completely hogs your storage space. As the architect, you have to weigh this out. You choose the algorithm based on whether your system desperately needs raw computational speed, or if you're working with severely limited storage. It's a real balancing act. Once that logic is fully verified and fine-tuned for efficiency, only then do we move on to steps 3 and 4 of our pipeline. We finally translate that beautiful language-agnostic logic into the strict syntax of a language like Python, C++, or Java. And in the real world, enterprise software goes through rigorous, multi-layered testing. You validate everything from tiny individual units of code all the way up to full user acceptance testing. Which brings us to our final section, Part 6, the architectural discipline. Final takeaways.
If you take away just one single thing from this explainer today, please let it be this. Problem solving is not about typing code. Honestly, anyone can learn programming syntax if they practice enough. But true computer science, the ability to analyze inputs, draft precise flowcharts, balance time and space trade-offs, and decompose massive real-world systems, that is the architectural discipline of thinking clearly. If you master the logic first, the code is going to effortlessly follow. So the next time you're facing what feels like an impossible challenge, ask yourself, are you just hacking away at the symptoms, or are you stepping back to architect the true logical solution?